the first example that we're going to be taking a look at, that we're going to be playing around with, is an investigation of the effect of aberrations on the focal region of linearly polarized LP fiber modes. The setup that we're going to be working with is this one. We start with a step index fiber as our source. Then you will see in the documentation, in the presentation, as well as in this particular use case, that later on in the use case we repeat the same experiment with a graded index fiber, but we start with a step index fiber here. And we can read on the slide all the defining characteristics, all the specifications of this fiber, the wavelength, the core diameter, as well as the two refractive indices that we need to define, to construct this fiber in particular, the refractive index of the core and the refractive index of the cladding. Then the light emanating from this source meets the first lens, which collimates the beam, and then we superimpose a certain aberration phase on this beam. The way we do that is with an idealized element, a functional element, where we simply define which aberrations and with what strength we want to use, and then they are simply on the plane where that component is located. Those aberrations are superimposed onto the beam that reaches that component. Then the beam, this time including those aberrations, propagates on to meet the second lens here, which focuses it onto the focal plane. And of course, the presence of those aberrations will impart a certain deformation to that focal spot. That is precisely what we want to investigate here. That's what we want to see, how that focal spot is deformed by the presence of these aberrations. Now, the experiment or the simulation starts by determining which modes propagate in our fiber. And to do that, we use the fiber mode calculator. That is the first new feature that we want to showcase, that we want to mention in the field of optical systems containing fibers. And this feature allows us to configure a specific fiber, both step index and graded index, and to obtain the modes that are propagating in it. So we're going to take a look at what this looks like, how this works in VirtualLab Fusion itself. We can already see the user interface for that calculator, for that fiber modes calculator on screen right now, but let's move on to VirtualLab Fusion to get a bit of a look and feel of how things work there. So here we are, this is VirtualLab Fusion 2021.1, and I have already prepared the files corresponding to this example. Among them, the first thing that we have discussed so far, the calculator, which you can see right now. And we're not going to go in detail through everything, we don't have a lot of time, but it's fairly easy to see that we have here the parameters of our fiber. We can select the mode type depending on whether we have a step index or a graded index fiber. We started with step index, so we select Bessel modes, and we see then that we have 6 propagating modes in our fiber, and we can read the characteristics of those modes here on the table on this right hand side: azimuthal order, radial order, propagation constant, and effective refractive index. This same information can be read in a bit more of a graphic form by clicking here on Show Mode Structure, and this is precisely the same information from this table. This graph can be a bit hard to read at first perhaps, but it contains exactly the same information here. We have as the abscissa the index of the fiber. We have 6 modes, so we would have points at 1, 2, 3, 4, 5 and 6, and then the different graphs show the information pertaining to the different columns that we have here: azimuthal order, radial order, effective refractive index, and propagation constant. The propagation constant uses the ordinate axis on the right hand side, all the other three the ordinate axes on the left-hand side. So if we wanted to read, for instance, I'm going to move the legend because it's blocking part of the information, and I can do so via the property browser, legend alignment, and here I can select a new position. Let's do top center. That gives us a clear view of everything. So if I wanted to read the propagation constant for the first mode that we, for the mode with index 1 that we're propagating, that is propagating in this fiber, I would go here to 1 and then find the red curve and read the value from this this ordinate on the right hand side. Then if I wanted to see the value of, say, the radial order for this very same mode, I would find the triangle, the graph, the line with the triangle pointing upwards. That gives us the radial order, and it would be this one, so it's index 1. That's the way we would read the information from this graph, and so on and so forth. So that is a different way of providing this same information. And then finally we can actually look at the modes. So we can create the fields, the fields that represent the different modes here. So I click on that button and we get a document containing our 6 modes, as we can see here at the top. We get information about the order as well, and we can go through them, see what shape they have. So these are the 6 modes that are propagating in our fiber. That is the first step of this example. Let's return to the presentation to see what else is in store. Now we know, because of this fiber mode calculator, which modes are propagating in our fiber, which modes are being delivered by our fiber source. So then we need to create the system with a source that generates this mode sequence, and then these modes which are generated by the source will propagate further in the system, as we have already described. And then, so this is what we already know, this is what we just saw. These are the modes that are generated by our source. We saw them with the fiber mode calculator. And then after propagating through the system, look at the arrow, how it indicates at which point in the system we are looking, or we're placing our detector. Then we can also see the result at the focal region, including that aberration phase and how what deformation that aberration phase imparts on that focal spot per mode, per fiber mode. But of course, the final result is a combination of all those modes. So we're also interested in seeing the coherent combination of all these modes that are being generated by our fiber. So at the top there we have that combination at the exit of the fiber, that would be the input plane of our system, and then at the bottom we have the final result, what the focal spot would look like, including all the modes that are being generated by that fiber, and with those superimposed aberrations on top. So all these results are generated with VirtualLab Fusion. Let's maybe take a brief look at how things go there. Here we are again. We have everything as we just left it a minute ago. I'm going to close this document containing the mode fields, and I'm going to minimize the calculator, and then we're going to look at the system. And sorry, that's the one for the grin fiber. Let's look at the one for the step index fiber, which is what we have been looking at in the slides. So we have 2 different sources here in our system. A fiber source, this will allow us to work with a single mode each time. And the multiple light source, let's double click on it. allows us to combine different individual sources, which in effect means we can include all those 6 modes that we know are being generated by a source in a single source. So we have here all those modes that we just investigated, implemented in the multiple light source. The multiple light source is incidentally also a new feature of this latest version, and the fiber source as well. So the fiber source individually, as well as the mode of combining the different modes together inside the multiple light source, are both new features of this version. So then we have all the rest of the system. We have our fiber end here. This is a surface that separates the fiber from the embedding medium, and then we have placed a detector here to look at the fiber modes as they leave the fiber. Then we have our first lens, this component that superimposes the aberration phase. Let's double click on that, take a look at which aberrations we're actually using. So here under physical parameters, we're using the Wernicke fringe type aberrations, and we can see what coefficients we're actually using here. So we have astigmatism in X and Y with different strength. We also have 𝘃𝗵𝗲 and Y, and that seems to be what we're using, the aberrations that have been defined here. So that is the way in which we define those aberrations that we want to superimpose on our beam. Then our second lens, and finally a detector at the focal position. So I can run the simulation with just this single fiber source. Remember, this just generates a single mode. In this case, the one with azimuthal order 1 and radial order 2. Let's take a look at that simulation with field tracing. And we're going to get 2 results, one for the fiber end and one for the position of the focus. So this is a fiber end, this is a mode after leaving the fiber, and this is a mode at the focal position, including the effect of those aberrations. I'm going to minimize these results, and I'm going to change the source that I'm using to include all the different modes that are generated by the fiber. And I run the simulation again, and this time we're going to get the full result, not just one mode, but the result including all of them, both for the fiber modes after leaving the fiber at the input plane of our system and at the focal position. Here, that detector that we have called diffraction pattern. And all 6 modes are being propagated and combined in a coherent way to produce the final result. And here we have it. Again, 2 results, 1 per detector. Here, the modes after leaving the fiber, and here that look at the focus, including the effect of the aberrations. That would conclude this part of the example. Then, as I said, we repeat the same procedure for a graded index fiber. We can maybe take a look at the results quickly, but we're not going to repeat the experiment in VirtualLab Fusion because the flow of things would be very similar. So we once again have an investigation of the modes that are generated by the fiber and their pattern, the diffraction pattern, including the aberrations at the focal region in the focal plane, and the combination, the coherent combination of both situations for the overall result. The second example in this content block devoted to fibers in optical systems will be an investigation of the effect of atmospheric turbulence on fiber coupling into a few mode fiber. the context for this example is free space optical communications. And once again, we use a scientific publication as our reference. The citation is, as before, at the bottom left corner of the page here. And let's investigate this sketch that describes the system that we're going to be simulating. So we start with a fundamental Gaussian beam as our input field that takes us to the top right corner of the sketch. So that's where we start, input field Gaussian. And then we collimate that beam using a lens, as is shown here. And then the effect of that atmospheric turbulence, of that air turbulence, is going to be simulated by using a phase-only SLM for different values of the strength, so to speak, of that atmospheric turbulence. And as we can read on the slide, d/r0, that parameter, is a typical way of evaluating the strength, the magnitude of that atmospheric turbulence. And we try with different values of that characteristic parameter. So by reflecting our input, a collimated input beam, on that SLM that is going to simulate the presence of atmospheric turbulence, we then propagate on towards a beam splitter that is going to allow us to look at the scattered field after the atmospheric turbulence, and another part of that beam, beam that has already interacted with the air turbulence, will propagate on towards the second lens that will focus it onto the entrance of a few-mode fiber. And then we can also investigate the output after the fiber, which has a length of 500 millimeters. Some additional parameters of a problem are also shown on this slide. Now, the new feature that we would highlight with this example, or that we want to highlight with this example, is the fiber coupling detector for multimode fibers. We've previously had a fiber coupling efficiency detector for single mode. Now we have this new added version that we use in this example. We can use 3D ray tracing to take a look at our system before performing the analysis to check that everything has been positioned correctly. And so that's what we can see on this slide. And then we perform the analysis, this simulation, for different situations: a single mode fiber, a 2-mode fiber, and a 4-mode fiber. So we can see the different blocks here for those 3 situations. Again, we use the mode calculator. We would use a mode calculator at this stage to determine the modes. And on this next slide, we investigate the results of that simulation. We can see and going downwards on this panel of results, these results are generated with VirtualLab Fusion 2021.1. Moving downwards, what we have is an increase in the strength of the atmospheric turbulence. Then the leftmost column corresponds to, as indicated by the arrows on the page, corresponds to the scattered field by the air turbulence. Then the second column corresponds to the entrance of the fiber. So this is what reaches that input position, that entrance position to the fiber after being focused by the lens. The scale of the result is indicated at the bottom row. And then as we move to the 3rd to 6th columns, we find the results after the light has propagated through the fiber, the 500 millimeters of the fiber. The loop in the fiber that is shown in the sketch is just to indicate the fiber, but it's not part of the physical system. The fiber would have a straight structure, would be in a straight line. And then, as I said, 3rd to 4th and 5th. Sorry, I said 6th before. third, fourth and fifth columns correspond to the results after propagation also through the fibre, and superimposed on for the different fibres that were investigated, single mode, 2 mode and 4 mode, and superimposed on those results we can read the values of a coupling efficiency which have been calculated with that new detector. Once again, the same experiment is repeated with a graded index fibre. The analysis would be analogous to what we have just done, so I'm going to skip it for the time being. If you're interested, again, you will receive all the documentation of the webinar so you can take a look at it yourselves. With that, we'll conclude the first block of content on fibres, as we have seen lots of exciting new features there, and move on to the next block, crystals and anisotropic media.